Okay, so we've reached a part of the course where we're going to start going through and talking about different kinds of circulations in the atmosphere. We'll start really big. We'll start with the global circulations, and then we'll work our way down to the kinds of circulations that govern our day-to-day weather, so specifically synoptic circulation, synoptic scale. And then we'll work our way down further to talk about thunderstorms, which is a type of mesoscale circulation. And so this will take us most of the rest of the course to get through all of that. Okay, so to get started, let's first talk about some directions, which we're specifically going to use to refer to directions that the wind is blowing. So some terminology for directions that we use in atmospheric sciences. There's two different ways of talking about directions in meteorology and atmospheric sciences. The first way is explicitly tied to directions on a globe. So specifically, if you're looking at a globe, you'll see that there are lines that run north-south from pole to pole. Those are lines of constant longitude. And then there are also lines that circle the globe in the other direction, and those are lines the east-west direction, and those are lines of constant latitude. Latitude circles and longitude circles. So there's then two different ways you can refer to directions, either along a latitude circle or along a longitude circle. The first of those is referred to as zonal. So strictly speaking, zonal means a direction parallel to your latitude circles. Parallel to your latitude circles, circles of constant latitude. But if you're at any given point on the Earth's surface, the direction parallel to the latitude circles is just going to be east-west direction. The latitude circles are at any given point on the Earth's surface are just going to run east and west. So for our purposes, we can take this term zonal to be synonymous for east-west, basically, along a latitude circle or east-west. Now, by contrast, if you're talking about a direction along a longitude circle, those are the circles that run from pole to pole, that's referred to as meridional. Meridional. The term basically comes from the term meridian, which is another way of referring to longitude circles. They're called meridians. You may have heard the prime meridian. The prime meridian is the longitude circle that has longitude of 0 degrees. Nowadays, that's agreed to be the longitude circle that runs through Greenwich, England, which is where there's an observatory where they had first sort of put this idea out, or standardized it anyway for nautical purposes. Regardless, this term meridional, strictly speaking, means the direction parallel to longitude circles, that is from pole to pole. But if you're standing at any given point on the Earth's surface, the direction parallel to the longitude circle is just your north-south direction. So we can take meridional to be synonymous to north-south. North-south. Now, we might use the zonal meridional terminology on occasion. I'll probably use it a few times in this lecture. But there's another set of terms that we use much more often that are much more explicitly tied to the map directions, north, south, east, and west. But there's one thing that we do, one twist we give it in atmospheric sciences that's slightly unusual. And so this is specifically when we're talking about winds, talking about the direction the wind is blowing. And the thing that's a little bit unusual is that normally we would think of, when we're describing directions, we describe the direction that we're moving in, right? If we're going towards Houston, then we're going south, southeast, basically. So we describe it in terms of the direction that we're going towards. But when we're describing winds, we actually do it the opposite. We talk about the direction that the wind is coming from. And the reason we do that is because, if we're standing at some point on the Earth's surface, the air mass that's coming towards us is going to be the air mass that we're going to see at some point in the future. So we're going to start to see properties of that air mass coming towards us and coming over us. And so we're more interested in the direction that the air mass is coming from, i.e. the direction the wind is coming from as the air mass moves, than the direction that it's moving towards. regardless, that's how it goes. That's how we roll in the atmospheric sciences. When we're talking about wind directions, we talk about the direction the wind is coming from. And specifically, the way this works is when we talk about the wind direction it's coming from, we'll go ahead and use that map direction and add the suffix early to the end of it. So for example, if we had the terminology, if we had the term easterly, a easterly wind, so we've got east here, and we added the suffix early, that's referring to a wind that's coming from the east. So easterly means from the east. Or for example, if we have the term westerly, it's the same deal. We've got west, we added the suffix early, and that means a wind from the west, from the west. Same deal for the other two directions, northerly and southerly. I bet you can guess those. For instance, southerly is going to be a wind from the south. Southerly is a wind from the south. Southerly, wind from the south. And of course, northerly is going to be a wind from the north. So that's how we do it. We take the direction the wind is coming from, we add early on the end of it, and that refers to a wind from that direction. So northerly is a wind from the north. So, for instance, let's suppose we had a wind blowing towards the east. A wind blowing towards the east. How would we refer to that wind? Well, if it's blowing towards the east, that means it's coming from the west. And so by our standard naming convention, we would refer to that as a westerly wind. So westerly wind, right, from the west. And alternatively, if we were talking about this in sort of the global scale circulation, context of global circulations, we could also use this terminology zonal and meridional. And if it's blowing east-west, that would refer to, if it's coming from the west, that would refer then to a zonal circulation. So we could call it and or a zonal wind. So we could refer to that wind then as a westerly wind from the west, or a zonal wind in the context of the global circulation. Note that the term zonal doesn't really refer to west or east per se. It's just the east-west direction along the latitude circle. You could say positive zonal is towards the east, and negative zonal is towards the west, if you like. Okay, so that's how we do it, from the direction the wind is coming from. All right, so let's start talking about the really big stuff, the global circulations. So specifically, let's suppose that we were an alien race, and our goal was to attack the Earth by releasing some sort of nerve toxin into the Earth's atmosphere. And so in order to plan our attack, we set up shop and watch the Earth. Maybe we're in the asteroid belt, say, so we don't draw any attention, and we're watching the Earth from afar. And so after a few days, maybe after a few weeks, we'd pretty quickly come to the realization that there's one big wind pattern on the Earth that is really dominant. There's one pattern that's really dominant, the dominant signal in terms of the winds on the Earth. And that dominant pattern looks something like what's shown in this figure here. So what this is showing is actually the average winds over 20 years. So we're trying to get an idea what the big signal is in the winds. And so we're averaging over a long time to sort of average out all the day-to-day noise and just leave what the big signal is, what the big pattern in the flow is. And so this is winds plotted here on the 500 millibar pressure surface. So remember that's sort of in the mid-troposphere. And so we're looking at this as if we're looking down from above on the 500 millibar surface. We've got the east-west direction here running along the bottom of the figure, and then north-south along the vertical axis with South Pole down here at the bottom, equator in the middle, and then the North Pole up here. And then what's shown is the winds here on this pressure surface. And again, it's the winds averaged over a long time period. It's actually about 20 years here, 1979 to 2001. So I guess that's 22 years, so that we get an idea of what the sort of dominant, robust signal is, pattern is in the winds. And the winds are actually shown two ways. There's actually little arrows in here. If you kind of look really closely, you can see that there are actually little arrows indicating the wind direction as well as how fast the wind is, bigger arrows meaning stronger winds. And then we've also got the colors, and the colors here are indicating the wind speed. They're indicating the wind speed, with the bluer colors being faster winds, the yellow colors being weaker winds, and the bluer colors faster winds. There's actually a color bar over here that tells you how strong the winds are for each color. And so what you see when you take the average of the winds is that there's two big currents. There's one current here in the northern hemisphere. It's winds that are blowing from the west towards the east. So again, we would name that a westerly wind, or more generally, it's a zonal wind. And then there's another one down here that's even more uniform, which is a current that runs from west to east in the southern hemisphere. So this then is the dominant pattern in the circulations on the Earth. You've got these two currents, one in the southern hemisphere and one in the northern hemisphere, and they're westerly. They're winds blowing from the west, and they circle the globe. And a couple things to note about this. The first thing to note is you'll note that these currents here on the 500 millibar surface are localized in what we refer to as mid-latitudes. That is, the winds are pretty weak here at the equator. There's not a whole lot going on at the equator. There's also not a ton going on right at the poles here. And it's really in between. That's what we mean by mid-latitudes, kind of in between the equator and the pole, these middle latitudes, where most of the action is happening. That's where we've got this current blowing around the latitude circle. And then the second thing to note is that it's a lot more uniform and also stronger in the southern hemisphere than it is in the northern hemisphere. That's really just tied to the fact that you don't have a lot of land mass in the southern hemisphere. The southern hemisphere is mostly just oceans, and whereas in the northern hemisphere you've got a lot of land mass, which introduces more friction, plus you have mountain ranges, which introduce some drag, and so forth and so on. So you end up with a faster jet and more uniform in the southern hemisphere, and a little bit more broken and weaker in the northern hemisphere. But regardless, it's still a pretty robust current running from west to east around the latitude circle. Okay, so that's what it looks like at 500 millibars, which is mid-troposphere. Let's suppose we go up to the upper troposphere now. So remember, upper troposphere, good pressure for that is something like 200 millibars. So it's the same kind of thing, same kind of map. East-west here on the bottom, north-south on the vertical axis with the equator in the middle. And it's also showing the winds, same thing as before. And again, you see that you get the same basic pattern. So when you go to the upper troposphere, you get these two currents. They're blowing from west to east, they're westerly. One in the southern hemisphere, one in the northern hemisphere, and they pretty much circle the globe along the latitude circle. Now, the other thing to note is if we go back and compare this to 500 millibars, so here's 500 millibars, here's 200, so this is 500 still, 500 mid-troposphere, 200 upper troposphere. Do it one more time, 500 mid-troposphere, 200 upper troposphere. What you see then is that the winds are a lot stronger in the upper troposphere. In both levels, mid-troposphere and upper troposphere, we've got these two currents in mid-latitudes, but they're stronger in the upper troposphere. So let's look at this from one more perspective. So specifically, let's suppose we take a cross-section running north and south. So this is going to be a vertical cross-section running north and south and up and down. And at each point along this cross-section, what we're going to do is we're going to take the average winds along that latitude circle. So it's going to be a cross-section showing the average, the east-west average of these winds. What's that look like? Well, that looks something like this. So just to orient ourselves here, we've got a cross-section with north-south here. So it's a cross-section running north and south. We've got the South Pole over here to our right, equator in the middle, North Pole to our left. And then the vertical axis is showing us up and down, but we're actually showing up and down in terms of pressure, keeping in mind that as we go upwards through the atmosphere, pressure decreases. I've listed a couple levels in here. So I've got the 500 millibar level, which corresponded to our previous figure. So that's sort of mid-troposphere. And then if we keep going up, we'll hit the 200 millibar level, which is upper troposphere. So again, north and south here, and then vertical. So let's take a moment to orient ourselves here. So if you've got south to our right, north to our left, and this is up and down, then which direction are we looking? Maybe I'll let you think about that for a second. We've got south to our right, north to our left. Which direction are we looking? Well, we'd have to be looking in the eastward direction, right? Because if we're standing in Austin, say, looking towards College Station, we would have south to our right and east to our left. Or north to our left. Have I been saying east? Hopefully I've been saying that correctly. But anyway, we've got south, if we're standing in Austin looking towards College Station, we've got south to our right, and to our left we would have north. So that's what we've got here. South to our right, to our left we have north. So we must be looking towards the east. We're looking towards the east. So what's shown in color in this figure then is the wind speed in this cross section, where we've got a color bar over here telling you the winds. The green values here, green and yellowish values, are values that are in the eastward direction, so the direction that we're looking. So if we put that into terms of our meteorology terminology, that would mean those are westerly winds because there are winds that are blowing towards the east. So saying that again, the green values are in the direction that we're looking, which was eastward, and so they are westerly winds from the west. By contrast, the blue values here go the other way, and so they must be easterly winds coming from the east. Okay, so with that, so what do we actually see in terms of the patterns, the main pattern in the winds? And so what you can see is the main pattern in the winds is that you get this really strong current of winds sort of in the upper troposphere level, kind of centered maybe at about 250 millibars, and also in mid-latitudes. So this is consistent with what we were seeing before on our two previous figures, where we've got the winds being very strong in the upper troposphere, and the currents associated with that are sort of maximized in mid-latitudes, maybe around 40 degrees north and sort of some similar latitude here to the south. Based on the colors, these are westerly winds here. So these are winds are coming from the west towards the east. And by contrast, if we look at the poles, well, at the poles, the winds are much weaker. There's a little bit going on, but not too much here at the poles. And if you look at the equator, Well, there's not a whole lot going on in the equator either. In fact, the winds are going the other way. They're coming from the east, so they're easterly winds here. But they're relatively weak compared to the winds we saw in mid-latitudes. So that then is the dominant signal that we see in the winds. We get these things, these currents, these very strong currents here in the upper troposphere, centered in mid-latitudes. So hopefully you've guessed by now that these two dominant currents of wind in the northern and southern hemisphere blowing around the globe on these latitude circles, those are actually our jet streams. They're our jet streams. So if you're watching the Earth from afar and you average over a long enough time to get rid of the sort of the day-to-day noise in the winds, what you find is that by far the biggest mean circulation in the winds on the Earth are the jet streams. These two very strong currents of wind blowing from west to east, circling the globe along latitude circles in the upper troposphere. So why is that? Why is it that the dominant, by far, the dominant pattern in the Earth's circulation, the winds on the Earth, are these jet streams? Well, it turns out that we can explain this pretty well based on things that we already know. So to see how this works, let's jump over to the chalkboard. Here, so I'm going to sketch out a cross section. So it's going to be another north-south cross section. And we're going to go through and do a little argument and see if we can infer why it is that we have these jet streams in mid-latitudes and why it is that they blow from west to east. So to start, let's sketch in the ground. There's the ground. And this is a vertical cross section. We'll orient ourselves the same way as before. But I'm going to draw this just for the northern hemisphere this time. The argument would be the same for the southern hemisphere, but in the southern hemisphere, some of the directions would be switched because remember the Coriolis force points in the opposite direction in the southern hemisphere. So let's just focus on the northern hemisphere and see how it works there. So if we're just doing northern hemisphere, then our cross section will run from equator, which we'll put on the right, to the North Pole, which we put on the left. So again, orienting ourselves, that means we are looking towards the east. We have south to our right and north to our left. Okay, and let's go ahead. We've done this before. Let's go ahead and say that the pressure at the ground, just to keep it simple, is everywhere 1,000 millibars, just to make it easy. Of course, the pressure fluctuates a little bit at the ground, but it's only a few percent either way. So let's just go ahead and make it simple and say it's 1,000 millibars everywhere. And then let's also go ahead and put in the temperatures in the lower troposphere. We know that the temperature near the equator in the tropics is going to be warm. And we also know that near the poles, the temperature is going to be cold. Okay, so now what we're going to do here, stepping forward, is show that just from this, just from knowing that it's warm in the south and cold to the north, that in itself is going to imply the existence of these jet streams. Nothing more than the temperature contrast between the equator and the pole. Now, the first step in the argument is actually something that we've done before, which is just to infer how the temperature, or to describe how the temperature is related to the height of the pressure surfaces. So let's pick 200 millibars, because that's close to where the jet was maximized. The jet was maximized somewhere around 250, but 200 is pretty close. So let's go ahead and pick 200 millibars, which is upper troposphere. Let's sketch in the height of the 200 millibar surface here in the tropics first. Let's just say it's here, 200 millibars. And let's do the same thing over here at the pole. keeping in mind that it's cold here, and so the layer between 1,000 and 200 millibars will contract because the layer expands where it's warm and contracts where it's cold. So we're actually going to draw it in at a lower height down here at the poles. And then in between, the temperature varies. It varies from warm over here to the south and cold to the north. And as the temperature varies, the thickness of the layer varies too. And so as a result, we get this shape of the surface, moving my pointer all over the place, that goes from higher heights here in the tropics and then sort of falls downward towards lower heights here at the poles. So maybe something kind of like that. So that might be the shape of our 200 millibar pressure surface. Okay, expands where it's warm, contracts where it's cold. Now let's go ahead and take some point in mid-latitudes because the jet was centered in mid-latitudes. So let's say maybe about there, say. And see if we can infer what the winds look like. See if we can infer the existence of the jet. And basically the argument's going to be very similar to the kinds of arguments we did before when we were looking at pressure maps or upper level charts and using the information about the pressure or the heights on the upper level charts trying to infer what the winds would look like. And the first step in that was to infer the pressure gradient force. And then assuming that we have large scales, the Coriolis force is going to roughly balance, and then we're able to infer the winds based on the Coriolis force. So we're going to do the same thing here. It's just that we're doing it in cross section. We're doing it from a side view instead of looking down from above. But it's the same idea. Now, when we're inferring the forces, though, one thing to keep in mind is that we're only dealing with horizontal flows here. We haven't talked about vertical circulations really at all. And so we're only talking about the horizontal forces and horizontal winds. So nothing up and down. It's only going to be, in this cross section, it's only going to be north or south because we're only dealing with the horizontal parts here. Nothing up and down yet. Okay, so let's start with the pressure gradient force. We have information about the heights of the pressure surface, and from that we should be able to figure out the pressure gradient force. Now remember, if we were looking at an upper level chart, the pressure gradient force would point from higher heights on your pressure surface towards lower heights on the pressure surface. Well, it's going to be the same deal here. Our pressure surface is going to have higher heights here to the south and lower heights to the north. And so the PGF, as sketched on this figure, must go from the higher heights in the south towards the lower heights in the north. And keeping in mind that we're just dealing with the horizontal force, nothing up or down, then we must have something like this. Right? Just the horizontal PGF, and it has to point from the side where you have higher heights on the surface towards the side where you have lower heights on the surface. Okay. Well, if it's a large scale flow, we know that the Coriolis force will come roughly into balance. And surely these jets are large scale. They're as large scale as you get. They circle all the way around the globe. So surely these guys must be pretty close to being in equilibrium with the forces, which means our Coriolis force has to balance. So Coriolis force, again, keeping in mind just the horizontal force, is pointing towards the south. Now, if we were trying to get the winds, well, now we have to infer the winds based on the relationship to the Coriolis force. Again, keep in mind we're only dealing with horizontal winds, so nothing up or down here yet. So only horizontal, which means north, south, into the board or out of the board. Nothing up or down. And so again, the rule is, if we're standing and looking downwind, then the Coriolis force is to our right. So in the present case, in order to get that to work, I would actually have to be looking into the board. The downwind direction would have to be into the board, so as to get to the Coriolis force to your right. If we're looking into the board, Coriolis force would be to our right. The way we represent that into the board on a two-dimensional sketch where I can't actually draw arrows into the board, the way we represent that is we put a circle with a cross in it, a circle with an X in it. That's going to represent a wind that's blowing into the board. So this guy is a wind into the board. That gives us our Coriolis force to the south. Now keep in mind from before that the direction that we're looking into the board was the eastward direction. And so if we have a wind into the board, the eastward direction is blowing to the east, which means it's coming from the west, which means it's a westerly wind. So a westerly wind. So just from the information, just from knowledge about the temperature contrast between the equator and the poles, we've been able to infer the existence of this westerly wind at upper levels in the mid-troposphere, which again is going to describe our jet streams. Now, one thing I should note about this is that in reality, so as I've drawn this, the contrast between the higher heights and the equator and then the lower heights of the poles is fairly gradual. But in reality, it often tends to be a lot more concentrated than that. So in reality, typically the equatorial zones tend to be pretty uniformly warm. The Arctic's going to be pretty uniformly cold. And most of the temperature contrast is actually going to be concentrated in the middle zones here. So right here in mid-latitudes, there's going to be the biggest zone of temperature contrast. It's going to be pretty concentrated in here. And that's especially true if you look on any given day. If you look on any given day, the temperature contrast tends to be concentrated into fronts. And those fronts are going to be really sort of concentrated here in mid-latitudes. So you're going to get a zone of pretty warm air to the south, pretty cold air to the north, and then you'll have a pretty concentrated zone of temperature contrast right here in mid-latitudes. And then by extension, if the temperature contrast is concentrated in mid-latitudes, then that's where the jet's going to live too. Because stepping through our argument from before, the argument was completely dependent on having a temperature contrast from south to north. And so if most of the temperature contrast is here in mid-latitudes, that's where the jet's going to be, in mid-latitudes. So we've been able to describe at least one of the properties of the jet, that we find the jet in mid-latitudes. We've also been able to describe, based on our simple argument, that the winds are westerly, which is another property of the jet. Now, the third property of the jet streams that we saw from before was that they're concentrated in the upper troposphere. So we've gone through and we've shown the existence of this jet in the upper troposphere. Now, from just this one surface, we can't actually go through and show that this is where the jet was maximized in the upper troposphere. But if you were to go through and do this argument for sketching other pressure surfaces, sort of one by one as you went up, you would find that the jet is actually getting stronger. The winds are getting stronger as you go up until you get to about 200 millibars. And so, in fact, the winds would, in fact, be maximized here in the upper troposphere. Now, above that, from the data, the winds actually started to decrease again as you go into the stratosphere. And the reason for that is because it turns out, so again, the jet is living based on these temperature contrasts. It lives on the temperature contrasts. And it turns out that as you get up to the upper troposphere, the temperatures actually switch. Instead of being warm at the equator, it's actually cold. The upper troposphere is pretty cold at the equator. And instead of being cold at the poles, it's actually warm. You sort of get everything switching in terms of the temperatures. And if the temperature contrast switches, then the whole argument switches. And instead of the jet getting stronger as you go up, it starts to get weaker. And so as a result, the place where the jet is strongest is right here in the upper troposphere. That's where it's going to end up being maximized. So just to summarize them, using nothing but information about the north-south temperature gradient, the north-south temperature difference, we were able to diagnose the existence of these winds in the upper troposphere blowing from west to east. That is, we were able to diagnose the existence of the jet streams. And since the temperature contrast is mainly concentrated between 30 and 60 degrees, i.e. in mid-latitudes, then that's where the jet's going to be too, because the jet was dependent on that temperature contrast. That's what the whole argument started with. And then finally, if we were to go through and repeat the argument, sketching in different heights, we would find that the maximum of the winds was localized in the upper troposphere, sort of around the 250 millibar levels, more or less. So just based on our simple argument, we were able to go through and describe basically all the properties of the jet stream. Specifically, we showed that the jet stream blows west to east, i.e. it's a westerly jet from the west. We showed that it's concentrated in mid-latitudes because that's where the temperature contrast is concentrated. And that it's strongest in the upper troposphere. Strongest in the upper troposphere. Those are the three properties of the jet to keep in mind. That it's westerly, it's in mid-latitudes, and in the upper troposphere. So this is the book's attempt to illustrate this in 3D. So we've got the equator to our right, North Pole to our left, just like before. So we're looking from west to east. And so we've got this zone of temperature contrast here, centered in mid-latitudes. And then above that, we've got our jet stream sitting sort of right above that zone of temperature contrast. Now again, the jet stream lives on these temperature contrasts. It kind of rides on the temperature contrasts, if you like. And it turns out that in reality, we often have two zones of temperature contrast. I'm going to go ahead and write this out and make a note of it. So in reality, we often have two zones of temperature contrast. We often have two zones of temperature contrast. On average, that's what you see. You have a weaker zone of temperature contrast centered somewhere around 30 degrees latitude, and then a stronger zone of temperature contrast sort of up in the 40, 50, 60 degree latitude. I've written it 50, 60, but it actually varies with the seasons. So you could probably say 40 to 60, something like that. And if you've got two zones of temperature contrast, then by extension, that's going to end up meaning that you have two jet streams. So this leads then to two jet streams. Two zones of temperature contrast, two jet streams. The weaker one, the one associated with the weaker temperature contrast near 30 degrees, is called the subtropical jet. So you have a weaker subtropical jet. And then the one associated with the stronger temperature contrast further north, that's called the polar jet. So you get a polar jet, and that guy's going to be stronger because there's a stronger temperature contrast. So you have a weaker subtropical jet and a stronger polar jet. So they've been illustrated here on this figure from the book. So this red band circling the globe is representing the weaker jet, the subtropical jet, and this blue band is the stronger jet, the polar jet. Now I've got some notes about this on the next slide, but I'm going to say the first few notes while I'm pointing at stuff on this slide. You can look at the next slide later if you like, but I'm just going to say these things as I'm pointing to the jets on this slide. And the thing I want to point out here about this is that it turns out that the subtropical jet, although it is tied to a temperature contrast, the temperature contrast associated with this jet is mostly just in the upper troposphere. There's not a whole lot of signal of this temperature contrast down near the ground. And so as a result, this jet stream is located pretty high in the atmosphere. It's a higher jet. It's located higher in the atmosphere than the polar jet. And in addition, it doesn't extend all the way down to the ground. So the signal associated with this jet isn't something that extends all the way through the troposphere. It's only located up at the top of the troposphere. On top of that, it's weaker because it was a weaker temperature contrast. Now, by contrast, so the subtropical jet is just an upper troposphere jet. There's no real signal down near the ground. By contrast, the polar jet, that is a pretty deep temperature contrast. The temperature contrast associated with the polar jet extends all the way down to the ground throughout the whole troposphere. And so as a result, this jet stream has some signal associated with it all the way down to the ground. You've got this westerly wind signal extending from the ground. It's pretty weak at the ground, but then as you go up, it gets stronger and stronger and stronger and extends all the way through the troposphere. On top of that, it's actually quite a bit stronger as well. It's additionally quite a bit stronger because the temperature contrast associated with this jet was much stronger. So if you put those two things together, the fact that the subtropical jet is weaker and doesn't extend all the way down to the ground, what you can infer then is that generally the polar jet has a much bigger impact on weather. The polar jet was stronger, it extends all the way through the troposphere, so it has a much bigger impact on weather. As well as on air travel as well. So we've got these very strong winds in the upper troposphere. That has a big influence on air travel. If I step back to the previous figure, so again, these guys are blowing from west to east. So for instance, if you look up average flight times from New York to London, say, you find that the average flight time in one direction is 6 hours and 50 minutes. If you're flying from New York to London, where is London? Somewhere over here. Then you find that it takes on average 6 hours and 50 minutes of flight time. On the other hand, if you're flying back from London to New York, you're going against the jet in this case, and it ends up taking you an extra 50 minutes. It's 7 hours and 40 minutes in that case. So clearly, whether you're going with the jet or against the jet has a big impact on your flight times. Okay, regardless, the polar jet's much bigger impact on weather as well as other things. And so from now on, we're pretty much just going to talk about the polar jet. We're kind of ignore the subtropical jet from here on. And whenever we talk about the jet stream, unless stated otherwise, we're going to be talking about the polar jet. One additional thing to point out here is that remember that the jet stream was tied to the zone of temperature contrast. Well, that zone of temperature contrast actually varies with the season. In the winter, it pushes way south. As the cold air works its way southward, the zone of temperature contrast is way south, as indicated by this blue curve here representing the position of the polar jet in winter. And then in summer, the cold air recedes and the zone of temperature contrast shifts way north, up here into Canada, basically. So we've got the jet stream then is going to shift with the temperature contrast north and south with the seasons. Now, this actually has implications for things, as we'll talk about later in the course. This has implications for things like tornado formation, because it turns out that in order to form tornadoes, at least the kinds of strong tornadoes associated with the kinds of storms we see in the Midwest, in order to form tornadoes, most of the time you have to have very strong winds in the upper troposphere for reasons that we'll see later. And that means basically most tornadoes, most sort of stronger tornadoes form underneath the jet stream, underneath a branch of the jet stream. Now in the spring, when we tend to have most of our tornadoes in the US, the jet stream is still pretty far south here. And so you can have tornadoes forming under the jet stream down here in the south. But as you move into summer, when the cold air recedes and the temperature contrast and the associated jet move northward, then you start to not have as many tornadoes anymore in the south, and any tornadoes that you form tend to be forming up here in the north, associated with the jet up there. We'll see that idea again when we talk about tornado formation. Finally, I should point out that on any given day, sort of what we've been looking at so far are averages, but on any given day, the temperature contrast can be, whatever it is on that particular day. It doesn't have to look much like the averages on any given day. And whatever the temperature contrast looks like on that day, that's what the jet stream is going to look like too. So this figure is just showing an example from when I taught the course a few years ago. It wasn't cherry-picked in any way. I just picked what was going on that day. And so this is showing the temperatures over the U.S. on that particular day with colder temperatures, purple, and warmer temperatures, yellow and reds. And you can see that most of the temperature contrast is in this zone here that kind of swings around the Great Lakes. So the Great Lakes are up in here. And you've got this zone of temperature contrast that's sort of swinging around the Great Lakes. Now on the next figure, I'm going to show the jet stream at, I think it was 300 millibars, so something close to the maximum jet stream height. And it's not exactly the same map projection, but I tried to make it as close as possible. So just to anchor yourself here, I'm going to put my cursor here. Maybe I'll do it with this finger. I'll put the pointer here sort of at the tip of, I guess this is Lake Michigan here, I believe. And we'll step this forward and look at the jet stream here. And what you see is that, in fact, the jet stream does follow this same kind of pattern, swinging around the Great Lakes here. And so what this illustrates then is that on any given day, your temperature zones basically your fronts will set up whatever they look like on that day. And whatever they are, to a good approximation, the jets at the upper levels are going to follow that temperature contrast. Because remember, the jet depends on the temperature contrast in order to exist. And so if we just look at the surface temperatures here, we can actually get a pretty good idea of what the jet is going to look like at upper levels. Sort of follows that zone of temperature contrast right through here. Now I'll note that it's not 100% agreement because the jet actually depended on the temperature of the whole layer from the ground up to the upper troposphere. And there are cases where the temperatures will be different sort of in the mid-troposphere than at the ground. But most of the time, it's actually a pretty good indicator. If you look at the temperature distribution at the ground and look for the zones of temperature contrast, that'll give you a good idea of where the jet's going to be at upper levels. Okay, so that's the jet streams. That's the main signal, the dominant pattern in the Earth's circulation on average. And the jet streams are east-west circulations. In the next screencast, we're going to show what the dominant circulation looks like if we just look at north-south circulations.